one on my left is Aizad bin Jamil. The second one is Arshad Sani. My name is Sahidan. And my right is Yuddin. The last one is Abdul Rahman. So our group discuss on the torsional vibration. Sure how what is our meeting and so on.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, I want to present about the torsional vibration. Okay, the torsional vibration. My objective group is to determine the risky rate, and the second is to determine the stiffness, and the third to determine the natural frequency. Okay, my group scope is the torsional vibration by using a Daisy lab and data equation hardware, and we use the sensor acceleration. That's all.
Okay, now we move to the setup. Our setup we use on the experiment is we measure the length of the rod. We use 6mm rod diameter. Okay, now this is the center of this with the weight the balancing disc of 500 grams. And we set up with the length of from this side to this side about 80 cm. Okay, we use the data acquisition system that measure the acceleration of the balancing. Okay, about the balancing specimen, we target we use a setup about from the balancer to the down plate is 27.5 cm with 500 gram of weight. Okay, this is about this the specification of this center balancer is 25 mm thickness, 40mm diameter, and with the mass of 2770 gram. Okay, this is a data acquisition. Okay, we plug in the sensor to the 0 point of the out of 4 slots, and we connect to the PCs.
Okay, now I will explain about the Daisy lab. Okay, first we need to set the sampling rates and the block size. Okay, for our project we set 2000 sampling rates per second and 4096 sample for block size. Okay, this is our block diagram. Okay, here is the input signal. Okay, the input signal that come up is acceleration because we use accelerometer. Okay, this is a filter. Okay, we need to filter to get the low frequency data because we need to filter the noise. Okay, then we use the data window and FFT is a fast Fourier transform to get the frequency domain and to get the spectrum. Okay, here after filter we integrate to the velocity to get the value of the velocity, and we need to filter it to reduce the noise, and we integrate it again to get the displacement. Okay, here the YT chart to show the graph of the acceleration, velocity and displacement. Okay, as you can see. Okay, here the graph. For the red one is the acceleration graph, the blue one is the velocity graph, and the last one, the pink, is the displacement graph. Okay, here the example. Okay, as you can see, it show the graph of the acceleration, displacement, and also the velocity. Yes.
The data are collected, and the data that we collected is first when we put on the Excel. First one is the mass that we use, and the distance. Distance is with the distance is the height from this point before we put on the load, and from this point to the ground, and the distance between when we put on the load to the ground. From this point to the ground when we put the load. And then here is the difference between the distance here, and the theta is the angle from this position, and we the angle when it get in inclined position. Okay. We collect the degree here, the angle here by using the Pythagoras theorem, and then when we get the degree, we convert it into the theta unit in radian, and also we we convert the radian in the mode of radian, in the angle in the mode of radian. We put here and we calculate here by the data here is for weight multiplied by radius of the center disk. Okay. Why we use this data is to complete the data to calculate the tau, and the data we use in the formula to collect the tau. The tau is in the y-axis, and the angle in radian we put in the x-axis. So when we put in the graph, we will get the inclined one. So the gradient is the stiffness of the for the basic equation that we use to find the decay rate. We use this equation, and we use to find the y value and the time value by using the YT chart in the DZ lab. And then this equation we use with the Lorentz function to eliminate the exponent. And then when we eliminate the exponent, we get the equation to this with C plus in the bracket minus sigma multiple with time. In the bracket negative sigma multiple by time is the gradient and we convert it into the equation of linear equation, which is equal to y equal to mx plus c. And the value of y that we get from the YT chart, we put it on here, and the time taken we will put it on here, and the value of y we use in the function of ln, and we get this value for the ln y. And for this graph, the axis is ln y, and the axis is for the time. So we get this point on the graph. So the gradient here is the decay rate for the experiment.
So as a conclusion, we almost achieve our target because due to the factor of the force we apply, so they are not the same as the different forces. So the data we collect almost precise, almost accurate as the analysis and the calculation. So that's all we going to conclude. So today, as a conclusion, after the various discussion achieve our objective and calculate about stiffness, our leak rate, and the load. After do some experiment, we can get most accurate, precise data, almost not the same, because of due to the factor of the force we apply, due to the position of the sensor, and the gap between the disc and the frame. So the data we calculate and the data we collect from the DZLab is almost the same, not accurate. So we almost achieve. We have achieved our three objective that we been searching to prove the torsional vibration. So that's all. Thank you.